We'll now continue our coverage of the role of mutable state in modern Java programs. In particular, we'll describe the benefits of applying shared mutable state to implement a memoizing cache. We'll also explain what a memoizing cache is. And then finally, we'll explore the Java-based design and implementation of the Memoizer class, which shows how shared mutable state can be used to optimize the performance in modern Java programs. We'll start by giving an overview of how memoization works. Memoization is an optimization technique that can be used to speed up programs through the use of shared mutable state. Memoization typically uses an atomic check-then-act operation to cache the results of expensive function calls. The pseudocode on this slide shows the signature and semantics of a typical method that implements memoization. This method is called compute if absent. It takes a key and a function. If the key doesn't exist yet in the cache, the compute if absent method performs a long-running function associated with the key and stores the resulting values in the cache using the key. It then returns the value that's been associated with the key in the cache. Henceforth, when the same inputs occur again, the cached results are simply returned. For example, if the key already exists in the cache, that cached value associated with the key is returned without performing the long-running computation again. We'll now discuss the design of a Java Memoizer class. The Memoizer class we'll discuss defines a cache that uses shared mutable state to optimize performance in concurrent programs. The Memoizer class is based heavily on the excellent book Java Concurrency in Practice by Brian Getz and his colleagues. The Memoizer constructor is passed a function. This function is stored in the mfunction field. The Memoizer later uses this function to produce a value based on a key. It does this by calling the get method, passing in the key. If the key has no value associated with it yet, then get uses mfunction to compute the value and stores it in the cache. If the key already has value associated with it, however, then get simply returns that value, rather than using the mfunction field to recompute it. This use of shared mutable state helps to optimize performance by caching the results of long-running functions. Internally, Memoizer uses a concurrent hash map stored in the mcache field to minimize synchronization overhead in concurrent programs. Concurrent hash map supports full concurrency of get calls and high expected concurrency for put calls. Moreover, contention in a concurrent hash map is very low due to the use of multiple locks, essentially one for each bin in the hash table, as described in the link at the bottom of this slide. In contrast, contention is much higher in other Java synchronizers, such as Java's synchronized map, which only has a single lock. Internally, the get method of Memoizer uses the concurrent hash map method compute if absent to ensure that the m function is called only once when a key is first added to the cache. In turn, the concurrent hashmap compute if absent method uses atomic check-then-act semantics to ensure that only one m function call occurs if multiple threads simultaneously invoke it for the same key at the same time. Now that we've given an overview of the Java Memoizer class, let's walk through its implementation. You can find this implementation in the memoizer.java class at the link at the bottom of the slide. We're now in the IntelliJ project for case study EX3. Let's take a look at the Memoizer class, which defines a memoizing cache that demonstrates how shared mutable state can optimize the performance of a concurrent Java program. An instance of Memoizer maps a key to the value produced by a function argument passed to its constructor. If a value has previously been computed, it's returned rather than calling the function to compute it again. The Java concurrent hashmap compute if absent method is used to ensure that only a single call to the function is run when a key and value is first added to the cache, even when a Memoizer is used in a concurrent and/or parallel program. This code is inspired by an example in the Java Concurrency in Practice book by Brian Getz and his colleagues. Memoizer is defined as a generic Java class that takes k and v parameters, which stand for key and value respectively. It defines a field called mcache of type map, which will be implemented by the concurrent hashmap class to associate a key k with a value v that's produced by a function. This function is also defined by a field in this class, and it produces a value based on the key passed to it. This function is passed as a parameter to the Memoizer constructor. It's stored in the mfunction field, and the new instance of concurrent hashmap is created and associated with the mcache field. The get method is the primary entry point into an instance of Memoizer, so all the operations described here are all performed atomically. There's also a remove method defined on a Memoizer. As you can see here, remove takes a key parameter of type k and calls the remove method on the concurrent hashmap to remove that key and value binding from the map. There are two other methods defined in Memoizer. Size returns the number of entries that are currently in the cache, and getCache returns the underlying map that's used as the cache. Now that we've walked through the implementation of the Memoizer class, let's wrap up this lesson on the role of mutable shared state in modern Java. Although there are situations where shared mutable state is helpful and necessary, such as the Memoizer example we looked at, you're generally much better off by minimizing and/or avoiding the use of shared mutable state in your programs if at all possible. If your Java programs must use shared mutable state, make sure to add the necessary synchronizers and/or use the appropriate concurrent or synchronized collections. There's a wide range of these synchronizers and/or collections, which are summarized on this slide. This YouTube playlist has extensive coverage of Java concurrent collections and synchronizers. So that's the end of part 2 of our discussion on the role of mutable state in modern Java programs.